Okay, so the big question we want to ask today is, when are two shapes the same, right? This is kind of the central question of topology in some sense. Topology, topos is shape, ology is study of shapes, and we will know when are two shapes the same. So here I have two different fonts, the bubble font on top and the, I don't know, basic font on bottom, right? And I want to have some way of knowing, like, well, this A is the same as that A in some sense, right? Like, this is represented as a bubble, this is represented in this more basic, just linear way, but they're both A's. And so we want to be able to detect somehow that these are the same shape. And likewise, detect that these are both B's and detect that these are both C's, right? So how can we do that? And one way to think about it is, well, this A on bottom is really just like the A on top if you squeeze it in, right? You can kind of imagine, like, if this A went on a diet, eventually it would become this A, right? So what might that look like? Something like this A, you can almost imagine superimposing it. You can imagine living inside of the A on top. So let me try and draw it there. There you go. And it's like, now there's a way to push all the points from the fat A onto the A inside. And in exactly analogous way, we could draw this B inside of this B, and there's some way to push all the points in a very natural way into that B, and likewise for C. Okay, so there's a name for this kind of move, and the name is a deformation retract. So a deformation retract will go from some space, the large space, the like bubble space, in this case I'll just note it by X, to a subspace, which we'll just denote by A. So here, like, the thin A is the space A, where the bubble A is the space X. Deformation retract is going to go from one space to another. What it is it's a continuous family of maps, F of T, where these maps are mapping the X onto itself, where T is just some value that varies from, say, 0 to 1 is pretty standard. We could pick some other range, but 0 to 1 is the standard one across the interval, 0 to 1, such that a few things are satisfied, such that we have three properties satisfied. First of all, let's make clear what I understand by a continuous family of maps. Here I'm thinking there's like infinitely many maps. The first one is F0, then a little bit later is like F.2, a little bit later F.5, till eventually you get to F1, right? So you have this series of maps ranging. And when I say the series of maps are continuous, when I say they're continuous, another way you could think about that is you could think, really there are two variables in this map. One is the point in X that you're at, and the other one is the time. And so you could think instead, if you prefer, this is getting a little bit technical, but you could think there's some big map F from, say, like X cross I to X, where you feed in some point of your space and the time you're at, and it spits out Ft of X. But what I want to emphasize now is it's continuous with respect to both of these variables. Continuous both with respect to the points in the space and with respect to the time. So there should be no big jumps from points that are close by, but also no big jumps from one f of t to another f of t close by. F of 0.5 should look a whole lot like f of 0.51. Right, or whatever close by means in this sense. You can make that rigorous with an epsilon delta definition, right, as you do an analysis. But your intuition is no big jumps in either variable, either in the space or in the interval. Okay, so you have this family of maps, continuous, varying continuously, and it satisfies a few properties. So let's list them. Property 1 is going to be at time 0, my map is just the identity map. So I'm going to use a black bold 1 to denote identity. If it helps, I'll put a little x here to remind you it's identity on the space x. So at time 0, the map just keeps everything at the same place. If I think about the bubble A as being my x, at time 0, everything is just held still there. But then, as time advances, by the time I get to f of 1, what it's now going to do is it's going to send the entire space x onto the subspace A. So all points in x get sent to some point in A, and everything in A gets hit. That's what I mean by this. So the image of all of x becomes all of the subspace A. And finally, the last property is going to be at every moment from 0 to 1. So t is an e-value from 0 to 1. If I think about what this map is restricted to values on A, so if I just ask, like, what is f of t doing at this point in A? Or what is it doing at this point in the subspace A? It is always going to be the identity on A. So decoding this, it starts off leaving everything in the big space the same. By the end, everything gets sent to the subspace. But at every moment, everything remains in the subspace. It's always identity for the points on the subspace. So if we want to kind of visualize what's going on here, maybe I can draw a clearer diagram of this. Let's think of what this map looks like at f of 0. Your space bubble A is going to remain just bubble A. You tell me, what is it going to look like when you're at time like 0.5? Yeah, it's going to skinny your bubble. So the way you should think about this is you can draw lines to the subspace that fill up this entire space A. I'll just draw a sampling of the lines here to help you think about what's going on. But any point in this big space X, bubble A, can be connected to the subspace via some lines. And you might think, if you're at the perimeter at time 0, you just stay at the perimeter. But at time 1/2, you've made it halfway there. And at time 1, you're now on the subspace. Or if you start out with a point that was halfway in, at time 0, it stays halfway. At time 1/2, it becomes a half closer, right? So everything is just moving towards the middle along some line. And so at time 0.5, the image of the entire space would be, as T mentioned, just a skinnier bubble, something hopefully a little bit like this. Until eventually, when you get to T at F at time 1, you have just your subspace. Is that good? Okay. Well, I guess what I should take a second to convince you of is maybe now you believe that this skinny A, the basic A, is a deformation retract from the bubble A to the skinny A. But I want to convince you, you can't do a retract from, say, like bubble A to C, to skinny C. So you might be like, why not? Why? So let me give you a non-example. Here's a non-example. Why is there not a deformation retract, say, from that A, from that bubble A, onto skinny C? Because you might be like, I can find a way to make skinny C fit in here. Like, we could just do that, right? And then why can't we just kind of deform the A onto that C? So can anyone think of a reason why this won't work?
A hole in the edge.
Yeah, in some sense you should think that's the problem. But why can't I just start drawing lines? You're right, that is the problem. But why can't I just start drawing lines? And start deforming this guy onto the C. When you think you understand something, it's really good not just to have examples of it, but to have non-examples, right? Examples that convince you. Why can't I do this? What's the problem? Continuity. So where's continuity violated?
You would kind of have to break it.
Yeah, like right here, right? You have these different lines, and some are trying to go to this point, and some are trying to go to this point. But what happens is you begin with 2 points that are arbitrarily close, but they'll get stretched in opposite directions. So if you think about your epsilon delta definition of continuity, you should be able to say something like, well, pick some epsilon that's less than the distance between these ends of C, pick some small epsilon, and then there should be some delta, so if two things are within delta, they end up within epsilon. But here you have points arbitrarily close that get pulled apart. So like the intuition for continuity is you don't have anything violent happening. Points close by should end up close by, but here points arbitrarily close by are getting pulled apart. So this is not a continuous. This would not be continuous. This would violate the continuity assumption. Okay. And maybe you can try to convince yourself similarly. You can't map the B onto a C or the B onto A, right? However, if you think about D, I could stick a D inside of here. You might think there is a sense in which perhaps the A and the D are not so different from each other. Right? Like, you can kind of turn A on the side and kind of round out that corner and maybe push that in a little bit, and that's a D. The D is essentially an A turned over and maybe extended a little bit. It's a kind of a stretch. But there's a sense in which A and D are similar in a way that perhaps B and C are not. Right? And so we want to build up to some way of describing a notion of same shape that allows us to say, A and D kind of both have one hole in it, C has no holes, B has two holes. There's some sense in which A and D should be considered equivalent. And so to move there, I'm going to slightly generalize this idea to the notion of a homotopy. A homotopy is, again, a continuous family of maps f of t from one space x onto some other space y. Doesn't necessarily need to be a subspace. And this is good, we're breaking away from the idea of subspace because the D isn't really a subspace of A. These are two different spaces we're thinking about. So let's try and find some way of comparing different spaces from subspace x to subspace y. And that's it. Where 0, where t is going from 0 to 1. This is a homotopy. And we will call the two n maps f of 0 and f of 1 homotopic. This is my notation for homotopic. Not quite equals, I did a little tilde shape on top, but it nearly equals. In some sense, they're equivalent. So I said this is a slight generalization of before. Here I had some family of maps. Here it was from X to itself. Now it's allowed to be between two different spaces. Here I had some conditions that it has to begin by being the identity. It has to end by mapping onto the subspace. we don't have all that. This is a much broader definition. So a deformation retract is a special kind of homotopy. This is a broader idea. But let me just give you some examples here to kind of build up your intuition of this. Your family of maps could go, say, from the unit interval into two-dimensional space. So you could have something like maybe F1 maps onto a nice little curve here. So F1 might map onto something like this. And, oh, we get a little rainbow effect. And let me make this F0 actually. F0, I'll have map here. And F1, I'll have map to some other map down here. So here I'm describing the map by showing you the image of 0, 1 inside of R2. Then these two maps are homotopic because there's kind of a natural way of sliding this guy into the other one, right? Like you could again draw lines between points, and at time a half, advance the points halfway along. At time, so maybe at time a third, looks something like this. So maybe this is like your f of 1/3, looks something like this, and say f of 2/3 might look something like this. Hopefully it's enough to see the idea of sliding it along. So here we'd have that your f0 is homotopic to f1. Although in fact something a little bit stronger is true here. As I moved these guys along, I left at all times these endpoints fixed. These endpoints never moved, right? So if I call these endpoints something like the point x and the point y, we can specify it's a homotopy that had the special property of never moving these endpoints. And I just say, I denote that by saying relative, sometimes just rel, the points x, y. You can think that back here, a deformation retract is a homotopy that has a special property that it's rel A. The subspace A never moves, right? So a deformation retract is equally just a homotopy, rel, relative, the subspace A. A never moved, well, the whole subspace. Here, it was just 2 points. So let me give you one more example. Let's say instead of wanting to map onto R2, I want to ask, is there a homotopy that maps S1, this is the circle, so I'm just going to map circles, a family of each mapping a circle, into the annulus. So here's the annulus. Center is missing, it's just this bit here. So the annulus is just the disk with an inner disk removed. So this can be thought of as, if you prefer to write it, as just S1 cross 0, 1, right? Remind you some of our notation from last week. Does there exist such a homotopy so that at time 0, you're this circle, but at time 1, you're this circle? So, is there any way to do that? You could do this if these were maps from 0, 1 into here. So how would you do it if these are maps from 0, 1 into here? Well, you tell me, like, what would it look like at time, point, 1/3 or whatever? If this is a map from 0, 1, this first guy I can think like maybe my 0 goes here, and then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1 goes back here, making a circle, right? But if I'm just doing maps from 0, 1, then these 2 points don't have to stay next to each other. My map at time, say f of 1/3, could look something like this. And then my map at time, say f of 2/3, I'm going to do quite a bit of work here, could start coming down and even bending over like this, f of 2/3, right? And so by the time you get to f of 1, you've now come back and closed into this other circle. So there was a homotopy here that accomplishes this. But there is no such homotopy. If I insist that they're all mapping S1 complete circles onto the annulus, so that your F0 is the yellow circle and your F1 is the blue circle. Because when I say this, this is saying that every step it has to be a circle. So I can't break open the circle like I did here. And you should think like, well, this yellow circle has a hole stuck in the middle. So I can't like drag it over the hole, because that would be leaving the space. But I need to stay within my space. I need to stay within my annulus. So I haven't given a proof for why these are not equivalent. But hopefully you have a bit of intuition for why they're not. And something we'll have to do, I don't know, maybe in a week or two, is try to get some methods to really see that there is not such a homotopy. But hopefully intuitively, you can see that there wouldn't be a homotopy if you have to keep the circle at every step, because he gets caught on that circle. He gets caught in this hole, right? Okay. So hopefully that gives you some sense of what we mean by homotopies. If you have any questions, just let me know. A homotopy is a continuous family of maps. It's saying one map is equivalent to another map. What I now want to do is translate this into a statement about spaces. Right now I'm just saying a map is equivalent to another map. And although I'm drawing pictures that look like spaces, really I'm talking about the maps. These are just the images of the maps. Now I want to say something about spaces. So here's the related idea for spaces. We call two spaces, x and y, homotopy equivalent. Homotopy equivalent if there exist maps, some map from x to y and some other map from y to x, such that when you compose the maps in either direction, you get something homotopic to the identity map. So we're gonna take a minute to address this. When you think about this first composition, first we do G, so it's sending y to x, and then f, x to y. So the composition is a map from y to y. So this first guy is saying it's identity on y, homotopic to identity on y. Whereas the second guy is first doing f, so it's going from x to y, and then y to x. So the second composition is a map from x to x. So the second one should be homotopic to identity on x. So here I'm just reminding you what this is identity on. This is saying everything on y stays the same, everything on x stays the same. And that somehow is homotopic to this composition of maps. So this might seem kind of confusing, but let's try and look at an example to begin to unpack it a little bit. So here's our example. I claim that the space letter C is homotopy equivalent to a single point. So here I really mean C as a space. So you often think of C as maybe the image of a interval in like two-dimensional space, but here I just mean that C itself is the space. This is a universe that only consists of the points making the letter C, and this is a universe with only a single point in it. And I claim the homotopy equivalent. So to see this, let's think about the two maps. First, let's think about F going from C to the point, and let's think about G going from the point to C. Now, you don't have too many options for these maps, right? Like this first map from C to the point, there's really only one thing to do. Send everything on C to the point. It's a really dumb map, right? Okay, how about the second map? What are we going to do to that point? Well, a point can't go to two different points, so there's only one thing to do. You send a point to your favorite point of C. I'll choose that point right there in the middle. Pick whatever point you want. But those are kind of the only two maps for us to think about, right? Now what we need to do is convince ourselves of what can we say about the composition of these maps. So let's first think about F composed with G. So let's think what happened. We have my point. I sent my point. So I took this point and I sent it to some point on C. That was the G map. So that was G. Now I need to do F. F is going to map onto the point. And where's it going to send that point? Well, there aren't really any choices, it just sends that point to that point. And so the composition is just a map that sends a point to a point. That map just is the identity map. F composed with G just literally is equal to the identity map on a single point. That's what identity map is. You leave the point the same, it's just a point. Okay, this is a dumb example. It didn't have to be equal to, it only had to be homotopic to, but here it actually was equal to, right? Now let's think about going the opposite direction. First we'll do the map F, which will take all of C and collapse it down to a point. So I take all of C and I collapse it down to a point. That's my map F. Then I do the map G that takes the point and just sticks it in the middle of C. So it takes that point, which is the image from before, and it just sticks it in the middle of C. Notice this composition is more interesting. The composition of G composed with F takes all of C and sticks it down at a single point of C. That is not the identity map. But I claim it's homotopic to the identity map. I claim that there's some homotopy, some family of maps, some family of maps H of T that maps C onto C. I'm just drawing the space. The name of the space is the space C. Some family of maps so that at time 0, this is the map that sends C down to just that single point. And at time 1, I want this to be the family of maps that's identity. I want it to be identity, so that would be sending C onto C. That's sending C onto C. I want it to be the identity map on C. So tell me, what is the homotopy? Like, what's this going to look like at time 1/2? What is H of 1/2? what would h of 1/2 look like?
You're taking all of C and mapping it to half.
Yeah, that's right. You know, it's like the way you travel from mapping C onto all of C to C down to a point is at various points you're just mapping to less and less of C or more of C, depending on which way you play the story. So at 1/2, you're just mapping C onto like half of C, you know, like half of C, right? And at time 3/4, it's 3/4 of C. Up until time 1, it's all of C, right? So there's a very natural homotopy here. So although this was not the identity map, we did have that G composed with F is something homotopic to the identity map on C. So whenever a space is homotopy equivalent to a single point, we call that space contractible. Now, in your mind, you should just think you can shrink the space to a point, right? But here's the way that we formally satisfy the definition. But just think homotopy equivalent to a point, shrink it to a point. So you tell me, what are some other points that are contractible? Some other spaces that are contractible. What else can be shrunk down to a point in a nice continuous way?
R2.
Sure, R2. Yeah, I mean, that first jump's going to be an infinite one, but you're right. R2 would be another example. So here are some more examples of contractible spaces, right? R2 is another one. Give me another one. Well, forget R2, we could make it Rn, right? It could be R3, R4, or whatever. What's another one? Yeah, disk. Certainly the two-dimensional disk would work, but or 3 or 4, whatever dimensional disk you like. So your disk also work. Think of any more. How about the sphere, like say S1 or S2? Does that shrink down to a point?
Depends on what it's embedded in.
Just the space itself. So I'm just asking, like, the space itself, is it homotopy equivalent to a point? So maybe this is worth going through the definition. I didn't plan to do this, but yeah, this is a really good example. So I'm going to erase this, and we're going to think about the sphere and try and see if we can tell an analogous story for S1. The question we have is S1, which is just the circle, not filled in, right? That's not the disk, it's just the circle. Is this homotopy equivalent to a single point? So we need our maps. So we need some map F and some map G. One that will go from the circle to the point, and one that will go from the point to the circle. But just like last time, these maps present themselves in the obvious way. The only way to send the circle to a point is just to send everything on the circle to a point. There's really no choice there. It's a Calvinist circle. Whereas the only way to send a point onto a circle is, well, you send it to your favorite point on the circle. Where do you want to send it? North, east, south, west, south. Oh, okay, if you insist. Sure, we can do that. And now we think about the compositions. So let's think about first F composed with G. So first this point gets sent onto the south pole of my circle. I don't know if you call it a pole in this case, but the south of the circle, the southmost point. And then, so that's the map G right there. And now we want to perform the map F, which sends everything to that point, including the south. So the south, again, gets sent to the point. And just like before, this is literally just the identity map. The point gets sent to the point. So F composed of G literally is the identity map on just the point. So we're happy with that. Don't even need homotopic, it's literally equal to. So very, very nice. But notice now what happens for G composed with F. First we're going to do our map F. So we're going to send the entire circle onto a point, and then we'll include that point back onto the circle. So we send the entire circle onto a point, but then the point goes to the south pole. So this is the map that sends the entire circle onto the south pole. And I want to know is there a homotopy? Is there a homotopy that moves you from sending the entire circle onto the south pole? This is your G composed with F. Like time 0 you're doing that, or time 1 you're doing that, whichever way you want to index it. To identity map. That's just literally leaving all points the same. Is there a homotopy between these? So let's just say for indexing that I want this to be my homotopy at time 0 and this to be my homotopy at time 1. Well, what's kind of the obvious homotopy you're thinking of? You just kind of start. So you would think like something like at h1 half, maybe you look something like the circle is getting sent on to just the bottom half of the circle. So this whole circle is getting sent to just the bottom half of the circle. Is this a homotopy? It's not continuous. Why not? Yeah? Yeah, these 2 points, pick points arbitrarily close to each other on top, get sent violently far away. Right? We shouldn't be separating points like this. Right? Now we're getting political. Leave points with their families, right? Don't want all these points in cages. Okay, never mind. So this is a violent action right here. This is not continuous. This is bigger than epsilon. Pick some epsilon smaller than that distance, and then no matter what delta you pick, you can find 2 points within that delta that get spread. This is the epsilon delta definition, but the intuition is just points very close by get pulled apart very far. We didn't have that problem with C. We do have that problem here. So S1 is not homotopy equivalent to the point. This isn't really a proof. We just show that the obvious thing doesn't work. You might want some justification for, well, why is there no possible homotopy? Hopefully this gives you intuition. We'll develop some tools to help us see why there isn't one. But the obvious thing at least doesn't work. And if the obvious thing doesn't work, then, what would? Question?
Why do we have to break the circle to get it closer to the point? Why can't we just shrink?
Because remember, this is a map. This map is this is going from S1 to S1. So we're not thinking of the circle as being embedded into R2. The circle itself is the space. So we're just mapping the circle S1 onto S1. There's no space in between here for us to work with. This is not embedded in some other space. That's the difference. Right here we're trying to think about just the spaces themselves, whereas over here we had this context of this map was mapping this into some other space. But now we're thinking this itself is just mapping S1 onto S1. So we're not allowed to move off of the S1s. Just working in the spaces themselves. Okay, great. Well, the previous example of mapping the C to the point, where we had that you could map that the whole space C is homotopic equivalent to a point, seems a whole lot like this idea of deformation retract. Right? Like, well, maybe it doesn't to you, but take a second, think about this. Is bubble A homotopy equivalent to little a? And what I want to argue is that yes, deformation retract is just a special case of this idea of spaces being homotopy equivalent. So here's my little lemma. If Y is a deformation retract of some larger space X, so here Y is a subspace of X, then X and Y are homotopy equivalent. So I'm trying to argue that this idea of homotopy equivalent is just an extension of the idea we introduced of deformation retract. So I'm going to do proof by example. But it'll be a really compelling example, right? And you can think of how you would generalize this to some other example, right? So let's just do this case of A. I was thinking through this, and I think I'm going to avoid some of the technical weeds of some of the definitions and work more on giving you intuition. But I'll try to do it in a sufficiently rigorous way that you'll believe me along the way. But I refer you to Hatcher's book for some more formal proofs of some of the things we'll talk about. I just don't want us to get lost in notation. More interested in you understand the notion than you tracking all the notation. So here I have the subspace A inside of the larger space X, which is bubble A. And I want to suggest that there are two natural maps between these spaces. So first, let's think about the map that goes from the space X, which in this case is bubble A, to the subspace. And then let's think about the map that goes from A to bubble A. Okay, so if you want to do this proof in general, replace bubble A with an X. Okay. Oh, what's the map that goes from all of A onto the subspace skinny A? What is that map?
F1.
Yeah, that is exactly this map right here. Just F1. That sends all of X onto the space A. Which, if I call it F1 here, we can get confused because I'm interested in a new homotopy. Here I'm just going to call it R for retract. So the R is just the retraction at the end, the retract of deformation retract. You're deforming down onto a retraction. So it's the last step, it's that F1 from over here. What's the obvious map for the subspace A, mapping it into the big space, big A? Well, you just put it in where it goes, right? It's like that subspace just sits in where the subspace sits. That's the inclusion map. So I'll denote by I the inclusion map, where the inclusion map is just including the subspace where it belongs, where it would fit. So it would be putting that A just right there. Now let's think about compositions of these guys. So let's first think about R composed with inclusion. So what does this map do? First is the inclusion. It includes A in big A. And then what does it do? Well, when it maps big A to A, this retract was defined so that it left everything in A fixed. Right? Like this includes time 1, it leaves everything in A fixed. So here the A just gets included inside of it, but then everything in here just gets fixed. So this literally just is the identity map on your subspace A. How about the other composition? I composed with R. So here you have the big space A. It gets pushed down, retracted onto the skinny A, and then A gets included back in. So what this map's going to do, this is a little more tricky. This is going to take the entire space A, so I'm going to denote all of this space A, and you're going to end up with, maybe I should color this yellow to denote, I'm taking all of this space A. And what are you going to end up with inside of big A? Just the A that sits inside. Now, this I composed with R is itself secretly just this f of 1. Right? This is just this I composed with R is just equal to f of 1 from the definition of deformation retract. Because that's what this does. It takes all of the space and sends it onto A. But here we had a homotopy F, where f of 0 was just the identity. So we have this homotopy. This f of 0 to f of 1 is just your homotopy. So your I included with R is homotopic to the identity map on the big space X, which for us is bubble A. So this really just falls out of this definition of deformation retract. So I'm trying to show that although this definition might look quite strange or different, it's really built just to be extending the idea of deformation retract. Okay. So here, looking at this theorem, you would think that deformation retracts are a special kind of homotopy equivalence. If you have a deformation retract, you have a homotopy equivalence, but there might be other kinds of things that are not deformation retracts that are still homotopy equivalent. And in fact, we've seen other things. So I've suggested before that we should probably think that like A and D are in some sense homotopy equivalent, these spaces, A and D. Now we could trace through this definition for A and D. I mean, we probably should. It would build character. But it would suck. Let's just do it for a few minutes and then at some point I'll give up. I want to argue that A and D, I want to argue that A is homotopy equivalent to the letter D. Okay, so I'm going to need you guys to help me with this one. Like, what is a map? Nothing fancy in this A, just A. What is a map F that sends A onto D? This is gonna suck. I have colors, that'll help us. How can we map this in a nice continuous way? Yeah.
We intend for the D to have the little legs.
Yeah. It's like, let's map this leg of A onto this leg of D. And let's map this like other leg of A onto this other leg of D, right? And let's map all these points on this line to all these points on this line. And let's map this top of A to the top of D. Well, this doesn't suck at all, because this map is in fact invertible the way I drew it. Right? As long as I don't compress any 2 points to 1 point, this is an invertible map. And so you can then, if this is your map F, you can just define G to be the inverse of this map. Oh, so that now literally your F composed with G is just identity. And your G composed with F is just identity. Well, that wasn't bad at all. Okay. This was a easy example because my D was literally just turning A on the side.
Doesn't that depend how you write the letter D then?
Right. If I didn't draw those little legs, it would suck, wouldn't it? Okay, so we should probably do one of those. Like A, I want to argue, is homotopy equivalent to D without the legs, or maybe just to like be, all the more clear to 0 or O, big O, right? D without the legs, big O, those are clearly equivalent to each other. Okay. So like if you can kind of just simply deform one to the other, we're good, but like does losing the legs make a difference? And here is we won't get identity this time, but we will get something equivalent to identity. So let's work this out. So I'm going to need more space. I'm sorry. We're going to have to create a little more space here. Let's first create a map F from A to 0. Help me out. Like, how are we going to do this? I don't know if this is big enough for you to see clearly. A to, let's O, 0, whatever that is. Let's say O. Well, one way to do it is just map this onto the circle, going around the triangle onto the circle, and this whole leg gets compressed to a little point. Everything, all those points on the leg get sent to that point. And all the points on this leg, can you see that different color green? Gets sent to that point. That's a continuous map. So all of these points get sent to those 2 points, whereas here gets sent to the stretch in between, the top gets sent there. And what is G going to be? Well, now we need to go from O to A. And now we have to be careful to keep this thing continuous, right? So we're going to do this in a couple steps. I'll send the top little arc of O to the top arc of A. But where's this next bit going to go? Well, what I'm going to have to do is map the first half down the leg. So maybe I should break it up into 2 halves. Map the first half down the leg, and then map the second half coming back up the leg. So as I move along my O, I'm going down and then coming back up. Then, I'm going to run out of colors. This bottom stretch can get stretched to this stretch, and this little next bit can take us down the leg. And this last little bit can take us back up the leg to connect with red, which continues back around. So as you go around the circle, you're mapping down, up, over, down, up.
Why couldn't you just map to the top of the A and then just the homotopy would just be collapsing the legs?
I'm going from 0 onto A.
Yeah, or so map the 0 onto just the top of the A without.
Oh, no, because I need to define a map from this space to this space that sends every point in this space to every point in this space. I need to cover every point in this space. Oh.
No, because at the point we didn't send it to all of C, we just sent
Oh, you're saying, yeah, you're saying I could just send the circle onto the top of A. Oh, that might make my life a whole lot easier. Yeah, because what I was about to do was going to suck. Let's double check. I mean, we'll have to think that this works. I'm just going to send this to this. Oh, I think you might just made my life a whole lot easier. Okay, let's think now about these compositions. Yeah, I think you're right. Which one do you want to do first? F composed of G? So what does F composed of G do? It takes the whole circle, it sends it to just the top of A, so that's my G, takes the whole circle, sends it to just the top of A, and then my F is going to send the top of A just back onto the whole circle with no, it's like there's nothing to worry about collapsing here, it's just sending it back onto the circle. In fact, that may just be identity. It may have got deformed a little bit, but if we did it, if we made that mapping consistent with that mapping, it's just identity. So F composed of G just is the identity map on the circle. Oh man, Alex has made our life so much easier. Whereas G composed with F is I first want to do the map from A onto the circle. So I'm going to do this funny thing where I map the top of A onto the circle. I collapse the left leg all to a point, and I collapse the right leg all to a point. That's my map F. And now I need to do my map G, which is going to take the circle, these points have been collapsed, and just include it into the top of A. And now, this is not the identity. This is not the identity from A to A. This G composed with F is mapping A onto just the top of A. So what's my homotopy? If this is going to be like my homotopy at time 0, what should it do? Eventually at time 1, I want it to send A just onto A. So what would it look like at time 1/2? Yeah, just little baby legs. Little baby legs, right? So as the time advances, you begin growing out the legs. Beautiful. So this is not equal to identity, but it's homotopic to identity. G composed with F is homotopic to identity on A. Okay, so this wasn't too bad after all. But there's an easier way. There's an easier way. And the easier way is to instead think back in this terms of deformation retract. So a deformation retract is an example of a homotopy. This is a homotopy that's clearly not a deformation retract. But notice that A and D are both, so this A and this D are both examples of deformation retracts from some larger space. So what is that larger space? Let's say like bubble A. Inside of bubble A, there is both an A that it deforms onto, but also inside of bubble A, you could have deformed it onto D. You could have deformed it onto D. Or you could have deformed it onto O. You could have deformed it onto O, where O is just like that O. Bubble A deforms onto any of those spaces. So here's my big theorem. X and Y are homotopy equivalent if and only if some space Z deformation retracts onto both. So let me try and give you a few more examples of this. Consider the space dumbbells and infinity. I claim these spaces are homotopy equivalent. Now, you could try to construct the map between these and argue, and that's a totally fine way, just doing the definition of homotopy equivalence. But easier, you could show both of these are deformation retract of the same space. And what could that space be that both of these are deformation retract of? Well, just a disk with two disks removed. A disk with two disks removed. Now convince yourself that this space does deformation retract onto here, that there's a nice continuous map, from any point of this space onto the subspace. So you need to take some time and think about this. And if it's writing this up, at least include a picture or something that shows you've thought about it, that this space really does, any point you're at in the disk naturally moves along these lines to some corresponding point on the subspace. So convince yourself that this disk with two subdisks removed really does deformation retract onto here. And likewise, it could also deformation retract onto this other space. So you can have a mental picture of how all the pieces move, maybe draw some lines to illustrate it. But having done that, you know now the homotopy equivalent. So you can kind of start thinking about the alphabet, and just any two letters you can organize into, tell me, what's another letter that's homotopy equivalent to A? Well, there's A, there's B. Those are going to be different because if the B connects back. This one has two holes, this one has one. And there's C, which has no holes, right? And D would be in this category. E would be up here. And well, what is this deformation retract of? Just a disk. There's a way just to move the disk onto here, or to move the disk onto here. E and F is up here, and G is up here, and H and I and J and K. These are all, well, they're all contractible. So they're all going to be equivalent to each other. J, K, L, M, N, O, P, Q, R, S, T. Okay, I'm done. So close. I think B's all alone, is it? Oh, that's sad. Okay, so you pick any two of these, and then convince yourself that if you have a disk, you could have your disk deformation retract onto any of these, onto G if you want to. And it's really? This whole disk can deformation retract onto that G? And it's yeah, you just have to convince yourself that there's a natural way of picking these lines that kind of tell you where things go. And you got to be a little bit careful about it, because it's points in the middle, where are they? And make sure you can do it in a continuous way. So this is good for you to think about. So take some time to think about how the disk slowly, and you could maybe draw a series of pictures of the disk moving in and becoming G, right, to help you. Okay, I think what I'll do is in the last 2 minutes, I want to give you one more way to think about homotopy equivalence. So one is you have the definition, two is you have this idea of deformation retract. There's a third one. And the third one has to do with quotient spaces. So let me just give you one more equivalent way, and then we'll be done with our discussion of homotopy equivalence. So here's my lemma. If you're given a cell complex, we defined those last time, X, with a subcomplex, this is something living inside of him, a subcomplex A, then I claim that this quotient map, which we talked about last time, the quotient map that sends X onto X quotiented by A is a homotopy equivalence. And maybe I'll just draw one example of this. So last time we actually saw this example. Last time I started by drawing this, we talked about quotient maps. I drew a sphere, and I attached to the North Pole and the South Pole a line. And this line, I'm going to call the subspace A. And I could also attach the North Pole to South Pole on the surface of the sphere. I'll call that line B. And the whole space is X. The sphere with the line attached to the North and South Pole. OK, there were two different quotients you could think of the space. One is X quotiented by A. And the other is X quotiented by B. What is X quotiented by A? Do you remember what it looks like? Quotient means you collapse that whole subspace A, the subcomplex, to a point. If this all gets pushed down to a point, what does this end up looking like? It's like a sphere where the North and South Pole come up and kiss. Right? So the North Pole and South Pole, still like a sphere, but they kiss in this point. The whole line A collapses to that point. Whereas on the bottom, if I collapse among B, what does this look like? Well, this just moves down, and the line connecting South and North Pole becomes a circle connecting at a single point. So this just becomes the wedge product of S2 with S1, a circle connected to the sphere at a single point, where B got collapsed down to. What this is saying is that X is homotopy equivalent to both of these spaces. And like maybe it's not obvious, but like what map would be the map from here to here? Well, exactly the quotient map is for that direction. And the map to go the other way, well, you know, this is a little bit tricky. So like trying to trace out the definition is worth doing, but try to like figure out like what are the maps to go each way and convince yourself it's homotopic to identity when you compose them. But if you can just show there's a quotient map, that's enough, this lemma is saying, to know there's a homotopy equivalence. But it's more than that. It's not just that this space is homotopy equivalent to X quotiented by A, and that X is homotopy equivalent to X quotiented by B. It's more than that. Homotopy equivalence is an equivalence relation. In particular, it satisfies the transitive property. So this is something you should take a minute to convince yourself as well. Like look at the definition, convince yourself it satisfies the transitive property. What that means is that if both of these spaces are homotopy equivalent to X, then they're homotopy equivalent to each other. And here's something where I think are somewhat challenging for you to immediately see, like in your mind. Like a lot of these other examples, you kind of have the intuition. Here it's probably quite challenging for you to have the immediate intuition for why these are homotopy equivalent to each other. But it follows from this collapsing. So you can trace it out, but here's another way to see homotopy equivalence. So we've kind of laid some of the foundation ideas now for algebraic topology. What we want to head to is the idea of fundamental group. So that's where we'll be moving in the next couple lectures. So we'll stop here for today.